All right, hello everyone. Today I'll be covering some design decision type stuff with sorting. So really, this design decision type stuff is like the type of question that you'll see on your exercise and also on like the exams. If we ask you like a sorting question, like a lot of the times we'll ask these like more design decision type questions. So like they require like knowing the sorts, so it's like super important to like look at the other videos if you still don't know like what the sorts are. But this is the type of question that you like will probably like most often come up in this class. So right now I'm just on this section handout here, and what we're going to do is we're going to take a look at this problem, sorting design decisions 2. And yeah, if you've already taken a look at your newest exercise, there's like a few scenarios that are like the questions on your exercise are like very similar to like stuff like this, where we like give you a scenario and we ask you like what sort should you use. So basically, what we're gonna do is kind of like talk about like how do you know like what sort you should use in each case. So feel free to like follow along, and like maybe take notes about like what your answers might be and see if they match up with mine. Yeah, the nice thing about these types of problems is like there's like no like one right answer I think for any of these. Like what matters the most is like your justification behind this. So basically, whenever you choose like a sorting algorithm for any of these, you wouldn't want to just list that sorting algorithm. You would also want to like list like I'm choosing this sorting algorithm because it has like these properties that I think are important for this scenario. So, like even if you write down like a sort that is like reasonable, but you don't give any justification for these types of questions, we can't give you like the full points because yeah, it's basically like all about the justification. So basically always include your justification when like presented with a question like this. And yeah, and we also, we ask for it in the title as well. So let's jump over. We have some slides for this. These are also linked on the course website. But yeah, we're basically going to kind of go over this. The other thing that I have too is previously in this slide deck, there was a chart linked. I'll go back to it. Where is it? We have this like sorting cheat sheet, and basically what I've done is I've just like taken a screenshot of this and put it up over here as like a reminder. Like this is what we have basically here. As you're working through these problems, like we don't expect you to like memorize all this stuff about each sort. So definitely feel free to like refer back to this cheat sheet for like a lot of these problems. It should be like super helpful and like probably a resource that you'll want to have like near you when you're working on like an exam or the exercise here. So let's go back here. Again, there's like a lot of stuff in the slides. You can totally take a look at all this other stuff as well. But yeah, we'll start off with these sorting design decisions, and we'll start off with A, where we say, suppose we have an array where we expect the majority of elements to be sorted almost in order. What would be a good sorting algorithm to use? So in this case, I guess we don't have like that much information about the scenario. Kind of the only important part, or like I guess one of the really important parts is basically that the majority of elements are sorted almost in order. So since this is kind of like the only information that we have about this scenario, we kind of want to like probably use this in our answer somewhere, right? Like in these scenarios, right, we're going to give you pieces of information and we'll basically be expecting you to like use each of those pieces of information in like your decision process for like what sort should I choose. So in this case, this is the only piece of information that we really have. The majority of elements are sorted almost in order. Sorry about the background noise. Try to talk a little bit louder. It's like really loud right now. One sec. So yeah, one sorting algorithm that we talked about that works well on sorted data, if you remember, is this insertion sort. In the best case, we have an O of n runtime actually, which is kind of crazy. And this happens when the data that you give insertion sort is already sorted. So insertion sort works really well. Like, so, even though the best case of insertion sort is like n, you should also kind of like know like where does that best case occur, or like where does this worst case occur. And there's also like section problems on this in this section handout as well, like that kind of go through like what does the best case look like for insertion sort or heap sort. But yeah, the best case for insertion sort is that all the data is sorted. You get an O of n runtime. So if we have data almost in sorted order, we should probably use insertion sort in this case. But yeah, you can see like maybe you could make an argument for like another sort, like these have good best case, worst case runtimes. But I think in this case, like the best answer would be insertion sort because you're using all of the information that we give you in the problem. Yeah. So, we have merge sort and quick sort as like predictable standbys, but insertion sort would give us O of n in the best case. Sorry, one sec. Let me shut this window really quick. I'll be right back. Okay, sorry about that. I was like really hoping that I could record this video with the window open because it's like such nice weather out, but apparently not. Okay, let's go through this next problem here. Okay, so for this problem, we have this prompt. We're writing code to run on the next Mars rover to sort the data gathered each night. So this is all the information that we have, but we have this hint here. Think about storing with limited memory and a limited computational power. So in this case, we kind of we have kind of like two things that we care about here. We want we want memory to be good, and we want the computational power to be good. When we talk about memory, usually what we're saying is like, we don't want to create like another data structure when we're doing this sort. So what you'd want to look at is, okay, if we wanted a sort with like good memory, good memory usage, we would basically look at whether or not it's in place, right? So if you remember, in place sorts mean like you don't have to have any auxiliary data structures to solve sort the data, right? If you're given like a list or like an array, you could just sort that like by rearranging the elements in that original data structure. There's no like copying over that you have to do. So if I wanted a sort that works with like limited memory, I would basically cross out merge sort now, because merge sort is like not in place, right? So merge sort uses more memory than any of these other sorts. So I'd basically cross that out and say, I don't want merge sort because it's not in place. Like it uses a lot more memory. And then I would think about, okay, so basically my options are down to insertion, selection, quick, and heap. Now I would think about, okay, if I had limited computational power, which of these would I want? Well, the in practice case for insertion and selection sort are n squared. So I might kind of like cross those out too right now. Like, if I have limited computational power, that means I want a sort that's fast, right? And, normally we want like a sort that's fast. So insertion sort and selection sort are kind of like those sorts, those n squared sorts. So I'd kind of cross those out now too, because it might not be the best to, pick these algorithms if we have like limited computational power. Like we want to take full advantage of that. So I'd be kind of like left down to like quick and heap sort. And honestly, I think for this problem, like you could pick either one of these is like good, right? Like, these are both in place, and these are both like have like good in practice runtimes. So I think like, if I was answering this question, I would make the justification, well, okay, we said that we want limited memory, so I need a sort that's in place, meaning I'm not going to use merge sort. I need a sort with that works with like limited computational power, which means that I would, eliminate insertion and selection sort, leaving with quick and heap sort. And between those two, I'll just pick one arbitrarily. But I would say like if you gave that justification, like you could use like any of these for the answer here. Let's go through this. So we want an in place sort. Let's see what the solution picks. So let's see. They picked heap sort basically in this case, but I also think like quick sort would be great as well. I guess in these problems, like we're asking you to pick like one sort. So if you're between two and they're like all else is equal, you can just kind of pick one arbitrarily and say that, heap sort's great because it's in place and it has a good in practice runtime. I think it's like perfect for this one. Cool. Okay. You're writing the backend for the website sortmynumbers.com, which sorts numbers given by users. Also, fun fact, you can actually go to this website. One of the former TAs for this class, made this website. So if you go to sortmynumbers.com, you'll see like a nice website that is basically like exactly the prompt for this problem. It also has like a pretty funny like FAQ page. So if you have some extra time, you should definitely check it out. It's pretty funny. Cool. But yeah, there's not like much given in this problem, right? Like we're just writing the backend for a website and it sorts numbers given by users. So again, we want to like make an argument for like why we're choosing a sort. So we should probably like figure out like, okay, basically out of all these like variables here, like which ones might be like important for this problem? Stable, in place, like, I don't know, like if there's like any, like great argument for these here. What I would say for this problem, it's like a little bit more subtle, but like I would focus on like this part which says like we're sorting numbers given by users. So, if a user can just give us like any numbers and they can, like use our website as much as they want, like the idea basically is that like they could be like adversarial and try to like give us a bunch of numbers that are like cause basically like the worst case runtime of our sorts, right? Like if we're just taking in like arbitrary data, like that's anyone can like make, somebody could like attack our website or, like make up a bunch of numbers that like trigger this like worst case runtime in our sorts. And basically if we're like running a website, we basically never want it to like go down or crash. No matter what anyone gives us, we want it to like stay up and, be functional for everyone else. So, a little bit more subtle in this case, like, but I would say like kind of the variable that we're gonna like want to optimize for is this like worst case runtime here, right? Like we want this website to be like always be working, always be fine for everyone, no matter what anyone gives us. So, somebody could be adversarial or, there could be like a lot of users using it and we just by chance hit the worst case runtime a lot. So I think like for this case, what I would do is like focus on the worst case runtime. In this case, the things with like the best worst case runtime are like merge sort and heap sort. And then again, right, like expect the worst. People might be malicious and try to submit like a worst case input. And so in order to protect ourselves, we're going to pick a sort with an efficient worst case runtime. Heap sort and merge sort, both great choices. I think you could pick either of those with this justification here. And that'd be great. So either of those would work. Cool. Let's move on to this fourth scenario. Your artist friend says for a piece, blah, blah, blah. She wants to make a computer that sorts every possible ordering of the numbers 1 through 15. So we're basically going to see every possible ordering of the numbers 1 through 15. And we want to know like what sort should be used here. So again, I would think about, okay, which of these kind of like variables, like worst, in practice, best, in place, stable, which one should we try to optimize for in this case? If we're sorting every single possible ordering of the numbers 1 through 15, if we're looking at all these variables, which one might we want to like focus on in this problem? I would say like, if we're going to sort every single possible ordering, probably the case that we want to like optimize for is like in practice case, because we don't really want to like, I would say we wouldn't really want to like optimize for like the worst or the best case, because like the worst and the best case are just going to be like one case out of this like all these possible orderings, right? There's like so many possible orderings in the numbers 1 through 15 that it doesn't really make sense to like optimize for the worst case, because like that worst case is only going to happen like one single time out of like all those possible orderings. So I'd say like in this case we'd probably like, want to optimize for like the in practice case, because like we're going to see every single input, so we want the sort that works best in practice. So if we're looking at the in practice case, I think that you basically take away insertion sort, take away selection sort. I think from that argument that you could say merge sort, quick sort, or heap sort would all be like I would like consider like correct answers for this problem with that justification. Like we want to optimize for the in practice case since we're going to see every single possible ordering. So I'd say like any of those three would work great for this. Let's see. So this means we're going to optimize for like the average case or like this in practice case runtime. And by the way, like just something to like note, which is like not super important. Like I think like, if you picked any of merge, quick, or heap sort with this justification, you'd be like completely correct. But it turns out that like in practice, quick sort has actually, really good constant factors for its like runtime. So you can think about like, asymptotically, quick sort, merge sort, and heap sort, they're all like the same thing. Like they're all like n log n. Asymptotically, they're not different. But remember for like asymptotics that we like drop those constant factors. So you can think of like, maybe quick sort's like 2 n log n, and maybe merge sort's like 10 n log n, and heap sort's like 10 n log n. In this case, like quicksort has a better constant factors, right? So asymptotically, not like better asymptotically, but like in practice, quicksort ends up like working really well. This is actually like the algorithm that a lot of coding languages like use to like implement their sorts with, which is actually kind of funny, right? Because it has the worst case runtime of quicksort is like n squared, but it still ends up like in practice being like a really good sort to choose for like just sorting arbitrary data. So basically, quick sort's n log n in the average case, and like as like an aside tidbit that we don't really like expect you to like know, it's like it ends up being like having like better constant factors than merge sort or heap sort. But again, like I said, I think picking any of these three for this problem you'd be totally fine with. But yeah, it's kind of interesting to know that like quicksort has like a really good constant factors in it. So yeah, so we chose quicksort because it has a good n log n average case here. Yeah. And then again, this is just like this note. Although heap sort and merge sort have O of n log n worst case runtime, they tend to be slower in the average case compared to quicksort. Of course, this all depends on implementation. And again, like not something that we're expecting you to know. So, you know, it's good if you know it, but it's fine to just like use the information that we have given you so far, of course. So yeah, okay. That's all the design decisions. Best of luck on your exercise and your exams.